Welcome to the morning session on Thursday. We will start with Yannic from TU Graz, and Yannic is going to talk about distributed symmetry-breaking.
Okay, thank you very much. And I'm very thankful for being here. I'm learning a lot, and I hope I can also tell you something interesting today. So let me specify the title a little bit. I will talk about delta coloring, and this is joint work with Manuela, Saku, and Yara. And let me highlight one person here, Magnus, because this is a long project going on over several years, and he's been the main character who's been on this with me for the whole ride. So let's start with the model of computation. So we use here the standard local model. So we have a communication network. We abstract it as a graph, and then the vertices in this graph, they communicate through the edges and discrete synchronous rounds. So in one round, a vertex can perform some local computations, exchange messages with all of its neighbors. So the message size here is unbounded, and the time complexity is the number of rounds until we've solved the problem, where every node here is responsible for their own part of the output. So a node has to, for example, say, I'm blue, I'm green in a graph coloring problem. And we do not charge for the local computations. And we will also talk about the CONGEST model, which is just the same, but now the messages need to be small. So log n bits, which is basically enough to fit a constant number of node identifiers. So what I'm interested in here in this talk is classic graph coloring, compute the proper graph coloring of this communication network. And classically, in this distributed setting, what we want to solve here is delta plus 1 coloring, where delta is the maximum degree of the graph. Note, this is very easy to solve in a sequential setting with the sequential greedy algorithm. Regardless of how you have partially colored the graph, you can always complete it to a full solution, just greedily when you're at some node. You have at most delta colors used by the already colored neighbors, you never get stuck. But today, I want to color with one color less, where this does not hold anymore. You cannot just solve it greedily. But what we know is from Brooks' theorem that any graph that is connected, not a click, not an odd cycle, has a delta coloring. So what's known about these two problems, delta plus 1 coloring and delta coloring? So delta plus 1 coloring has a lower bound of log star n. This is basically the paper that started this whole area. And I'm only talking about randomized algorithms here. And delta coloring is much harder. It actually has a log n lower bound. On the upper bound side, we have sublogarithmic time algorithms for delta plus 1 coloring, so polylog log n, and we do have them in local and also got them recently in the CONGEST model. While for delta coloring, well, also for randomized algorithms, before this work, we only had polylog n round algorithms, and in CONGEST, there was no algorithm at all. So what we wanted to answer here, and we thought we would just write one paper on this and be very quick, was to just get a sublogarithmic time delta coloring algorithm here that optimally also works in the CONGEST model. Yeah. So let me give you a bit more background because I get this question quite often. Why do you now care for coloring with one color less? But from this distributed point of view, this is really a fundamental difference. Merely for what I've already said, that if you want to make large progress in a distributed algorithm, you want to color many nodes in parallel and then complete the coloring in the middle, for example. But for delta coloring, if you just do this in a naive way, you may run into a situation where you cannot even solve existentially, complete the coloring to a full solution. So this delta coloring requires new techniques compared to this classic greedy problems like delta plus 1 coloring, maximal matching, maximal independent set. And it also has been a host for such new techniques. And it's also, for me, it's a prototypical problem for what we do not understand in this field. And let me elaborate a little bit on this. So this is the complexity landscape of local graph problems, local constraint satisfaction problems on bounded degree graphs. We won't talk about bounded degree graphs today, but this is the motivation, or one of the motivations for me to understand this problem better. And what you see here, whenever there's a dot, you have a problem that has this complexity. So here, this area is dense, but you also have these big X's, which means, for example, there's no problem which has complexity square root of log n. So what you see here, delta plus 1 coloring on bounded degree graphs is really easy. It just logs star rounds. And this is fairly well understood, except for one regime, the one here in the middle. This is what we don't understand. And delta coloring is the only natural problem whose current upper bound on bounded degree graphs is just in this regime. So this is bounded degree graphs. That's why the state here for delta coloring is polylog log n rounds. Okay, so this motivates the work. And yeah, before we actually go into solutions, let's have a short recap or a high-level overview of previous algorithms for this problem that are polylog n rounds. So in a very high level, polydelta. No, because of the lower bound of log n, you cannot have it. You cannot have it, yes. Yes, so let's look at what these previous solutions on a very high level manner work on. And very high level, they need one definition. This is the definition of an easy component. This is an induced subgraph in which you can never get stuck. Regardless of how you color it outside, you can always existentially complete the solution in this subgraph. So these are well studied under the name of degree-choosable components. And what we showed a few years back is that every node in a graph is contained in such an easy component with a small diameter. And small diameter is very helpful in the local model because it allows you, in diameter time, you can brute force any solution. And then you can put a lot of machinery on top of this to actually get polylog n time algorithms. But if we want sublogarithmic time algorithms, we need a different approach. And in particular, if you also want something that works in CONGEST, we cannot brute force solutions in diameter time and even learn these large diameter subgraphs at all. It's completely infeasible in CONGEST. So we need a more direct, more local approach here. And if I summarize all of our work on one slide, the more local approach and the most natural that we want is slack. We want to generate slack in the graph, which then essentially brings us back to the greedy regime. So what is slack? The slack of a node is the number of available colors that it has minus the number of competing neighbors. Right? Initially, a node of degree delta doesn't have any slack because you have delta colors available and delta competing neighbors. If you're a node with small degree, you have slack because you have fewer competing neighbors. So that node, you could sequentially greedily solve the problem for such a node. And also, if we manage to color two neighbors of a node with the same color, we get slack at node V, because now it just uses one available color, but two competing neighbors. So the bottom line here is, whenever nodes have slack, we can solve the problem with a greedy approach. We can use existing methods to actually solve it. So what we actually need to solve here is degree plus one list coloring. It's well understood. And once we have slack for nodes, this problem is easy. So what we focus on for the rest of the talk is actually to generate slack for nodes, and how do we do it? And because this is a short talk, we're just going to do this in a simple case, but which already shows you some of the challenges that appear here. We just want to generate slack in sparse graphs. So sparse graph is essentially one here where a node has a lot of missing edges. These are all missing edges here in its neighborhood. A lot of the challenges with delta coloring appear in the dense part, but I think this would take another 10, 20 minutes to talk about the dense part here. And I think for the sparsification part, this is already quite interesting. So what's the core subroutine to generate slack in a sparse graph? It's this very simple randomized one-round algorithm in which every node activates itself with a constant probability and then picks a random color and keeps it if there's no conflict, meaning, so you send it to your neighbors, you receive their colors, and if no one tries to get colored with the same color, then you keep it, otherwise you discard it. So one can show that each node gets colored here with constant probability in this algorithm. What's more important for us here is if a node in its neighborhood has a missing edge, then the probability that both of these nodes get the same color is proportional to 1 over delta. Basically, intuitively, if you ignore all dependencies with probability 1 over delta, they pick the same candidate color, and they can also keep it with a constant probability. So if a node has many non-edges in its neighborhood, you also expect to get quite a bit of slack from that. And what one can show is that despite dependencies, this is well concentrated. So the probability for a node to not have slack is exponentially small in delta, in a sparse graph. Here.
Are you looking at particular range of delta being small?
That will come next, yes. So this is super easy if delta is large, right? If delta is large, you just do this one round algorithm, and this will turn into, with high probability guarantee, you do a union bound over all nodes, and you immediately get slack everywhere. So you can summarize if delta coloring is easy in the sparse parts, if delta is large. In our work, we also extend all of this to the dense part, which needs a lot of work, and in the end, we actually obtain for large delta a log star round algorithm. We can later talk why this does not contradict the log-log-n lower bound. But for this talk, what I actually want to talk about is a different range of delta. And this is the most challenging part in all of this work. So what I'm assuming now for the rest of the talk is a delta regular sparse graph, and that delta is small. So it's in the sublogarithmic regime. And then if you go back to this slide, then clearly this one here does not give a with high probability guarantee. You have some pretty good local failure probability, but it's not a with high probability guarantee. So we need to do something smarter. But what we can do and show that we can at least, with these local failure probabilities, they really call for the Lovász Local Lemma. Because with that, we can at least show there exists a solution to the random variables of this one round algorithm here, such that everyone gets slack. So who here knows the Lovász Local Lemma? That's great, that's essentially everyone. So we can be fast on that. So how do we model the slack generation problem as an LLL? So we introduce this bad event for each node that holds if the node does not have slack. We have these random variables for each activation and candidate color choice of each node. And what we've seen is then the probability of a bad event is exponentially small in delta. And for LLL, what's also important is how do these bad events depend on each other? So what's the dependency degree here? So what you notice if whether a node gets slack depends on the randomness in its two-hop neighborhood. Because whether you have slack depends on the final color choices of your immediate neighbors, and whether these immediate neighbors can keep their color depends on the randomness in their neighborhood. So whether a node has slack depends on the two-hop neighborhood. But if nodes are a few constant hops apart, whether they get slack or not in this one round procedure here is independent. So the dependency degree is at most polynomial in delta. So what we get here is that P times D is much smaller than 1, and LLL tells us, okay, there is a variable assignment avoiding all these bad events. This is not really surprising because, well, we could also use Brooks' theorem to show existence. Brooks' theorem gives us a delta coloring of the graph, and you see in the delta coloring of the graph, every node of the degree delta must have two neighbors which actually have the same color. And we could just use that as a variable assignment. So existence here is really not very useful and not very surprising. But we will use LLL to actually compute a variable assignment, so to compute this slack. So what we want to do here, we want to use the constructive LLL. And which algorithms exist here? So there are logarithmic time algorithms for LLL. So most famously Mozart-Tardosh, or the more efficient distributed implementation by Chung, Petty, and Su. But they're logarithmic time. And we also have some sublogarithmic time distributed algorithms. But unfortunately, none of these is sufficient for our needs here. Actually, these sublogarithmic time algorithms here, all of them, or most of them, have actually a polynomial dependency in delta in the max degree. And now if, for example, delta is square root of log n, then this polynomial dependency on delta will not give us a sublogarithmic algorithm. So we want to do something different. So what we want to do is we want to follow the blueprint for almost all sublogarithmic time algorithms in this field, and they all use one technique. This is the so-called shattering technique. So the shattering technique has two phases. In the first phase, you use the randomized algorithm to solve the problem in almost all parts of the graph. So in all these gray parts, you've solved it, and it's fairly standard by now to show if this algorithm has good local failure probabilities and what happens far enough in the graph is independent, then you actually only have these small islands of small components left here. And then in the second phase, you use a cleanup algorithm to solve these unsolved parts. And what you now use here, and why this algorithm is fast, is that they are small, so you can replace the n, for example, in a deterministic runtime, you can replace the n with an n that is exponentially smaller, give you faster algorithm. So for example, for the state-of-the-art delta plus 1 coloring, we have this runtime, which has these two terms. One is this pre-shattering phase, log start time, and here, this is from the cleanup phase. And we want to follow this blueprint here for our LLL or slack generation. And I'll use both of these a bit interchangeably now. So what could we use in this first phase as our randomized algorithm? Well, the best take that we have is we just flip all the variables according to the distribution. Because of the good local failure probabilities, most of the bad events will be avoided. Right? What one can show easily here is that all the problematic events, they form small connected components. So how about just using a deterministic LLL solver? We can take these off the shelf, they exist, to finish off these small components. Yes.
And are its neighbors and two-hop neighbors part of the component?
Its variables are part of the component. Yes, its two-hop neighbors, all its variables are part of the component, yes.
And how far do you go? Just two hops?
Just two hops here, yes. Yes. Except that then other nodes also see, yes. Yeah, you just go two hop, yes.
So any vertex which has not received, any vertex didn't get, any vertex that didn't get a slack in its neighborhood and its two-hop component, you put a graph, and these components are connected components of that graph.
Exactly. Yes. Right? Yes, and optimally, we would just now want to solve these small components fast. But how can we do this? Because now already, if you think of general LLL terms, we cannot even solve this because all the variables are already set from our initial flip. So for some events, there's no way of just retracting and reassigning variables. But if you now retract the variables, this may make other events unhappy again, and this may propagate. So the very high-level solution here that we have is very simple. Basically, two chances are better than one. How about you only flip half of your variables in the first case? And I think it's best to understand this with the slack generation example. If you, for slack generation, had two different sets of neighbors, you could use the first set of neighbors for the pre-shattering phase and the second set for the post-shattering phase. So this is what we want to do. We first split the graph into two sets such that every neighborhood is split. And then we use the first set in the pre-shattering phase and the second set in the small components. Right? And the node really doesn't care whether it gets slack from the first set or the second set here. So once we really have these sets, this is really straightforward in the local model. Because we can use this off-shelf solver for these small components. And there's not much that we need to do here. But the question is, how do we get the sets and what do these sets have to satisfy that all of this works? And this is why I'm presenting this here. So one part that we need is that the graph induced in each neighborhood of these sets still needs to be sparse. Because non-edges that go between the parts essentially don't help you here. So what you need is that these sets still preserve the sparsity. And another one, even so it's a title of the talk, I don't even have a slide on this here, is that in CONGEST, we also want each node to have few neighbors in these sets. So we want to have a small degree, these sets should be small degree and be much sparser. What's the intuition why we need this? We mainly need it in this post-shattering phase, and as we've already seen, an event depends on its two-hop neighborhood. And in the post-shattering, we want an event node to learn a lot of information about its random variables. If such a set Si has a large degree, an event node cannot even learn information about all of its variables. And this is really helpful here if we sparsify it to a small degree graph, because then an event node can learn a lot of information about all of its variables. What we will eventually do, we will compute like a small set here and another small set, and most of the graph will not even participate. So it's not as the picture suggests a nice partition, but we will have two very small degree sets that we will use.
But they have to be lower. Okay.
Yes, so they're very small degree, but still have enough non-edges.
And a small is like log n.
Polylog, actually. So very smallish. Yes. So the question is, now how do we compute these sets?
Are you computing different S1, S2 for each vertex?
No, we globally compute one S1, which should satisfy the properties for every vertex. And we globally compute then one S2, which also should satisfy all the properties for all the vertices.
And then, like, is it specified how you color the S2?
Once everyone has slack, so then we run this procedure, then we've only colored some of the vertices in S1 and some of the vertices in S2. But what we will guarantee that after this step, everyone who's not colored will have slack. So afterwards, we just finish it off with degree plus one list coloring. Yes. So the rest and the main challenge is actually how do we compute these sets? So how can we get this sparsification, which has a low degree, but still many non-edges. And yeah, what you can observe that this is an LLL itself. Right? If you just sample every node into the set with probability Q, for a non-edge to be in this induced sample, the probability is Q squared. So you expect a Q squared of your fraction of your non-edges to be in the sample, and degree reduction is also easy. And both of these are actually concentrated. There are lots of dependencies in the first one, but one can show that both of these are concentrated, and the probability that such a random sample for a node is not good in the neighborhood of what specific node is again exponentially small in delta. And for this illustration here, I think it's best to just assume this Q is constant. This is not what we will do later, but I think this is best to get the feeling for it. Yes. Such that it just works, yes. So what we can summarize here, that sampling such a degree-bounded sparsity-preserving set actually is an LLL, but it's a very specific one. Right? It's a binary LLL sampling variables true, false, and we have opposing monotone events. Right? So we have this event which prefers to have more nodes in the sample, and this event which prefers to have less nodes in the sample. And this is what we want to solve, and this is what we generally solve. And we stick to the same blueprint. First, we want to have this shattering approach. So first, we flip all variables, and then for the vast majority of the bad events, the sampling will look good. We have enough non-edges and also a small degree here. But for some events, the sampling doesn't work. For example, we have too many neighbors in the sample. So the only thing that we can do here is we need to retract all of them. So our second step is, to retract all the variables here. And as said, such a retraction now can propagate. So here we have a node that prior was happy about, now it saw a single retraction. And this is the situation that we cannot just send to the post-shattering phase. Because now, with the single retraction, the only way to make this node happy again is to include this node into the sample again. This is a very hard constraint. And yeah, you can easily create some situations where you even have a subproblem that is not even solvable here. So what we do here, such a node that sees the retraction of the first kind, does a second type of retraction, but this is a very asymmetric retraction. What it now does, it retracts all of its not sampled variables, all of the false variables, giving it a lot of fresh randomness. This is really asymmetric here. But once we've done this, we go to the post-shattering and there are no more retractions. So what we see in the post-shattering, we have one of these three situations. Everything was good, so we're not even participating in post-shattering. We're in the situation, everything is retracted, so we're in the original LLL situation. This is easy what we can solve. Or we're somewhere in between. And now what we see here is, at least for the event of sampling non-edges, this situation is better than the one that we started with on the left, because we already included some vertices in the sample. This can only help because it's a monotone increasing event. So this is essentially our general LLL solver. And yeah, we make this more general in the paper and define a notion that we call the risk of an LLL, which basically describes the worst case scenario that can happen in the post-shattering phase for an LLL. And what we've just seen is, if you have a monotone increasing event, you always have a low risk. The post-shattering case, actually the worst case is if all your variables are participating, and this is the original LLL. So this is very helpful, that monotone increasing events are very easy to deal with. Of course, a sampling process which only has monotone increasing events is very boring, because you can just include everyone in the sample and solve it. So one should usually compose it with a monotone decreasing event, and there one needs more work. So for example, for this degree bound, you can just have a separate bound of a degree in the first phase and the second phase, and you're done. And they just add up. Yeah, and as usual with LLLs, one can mix and mingle events. So this is a bit technical, but yeah, in my opinion, it's still simpler than prior approaches to this, and it subsumes and generalizes quite a few of them. So let me summarize. What we have here is two LLL solvers. The first one that solves LLLs which have two of these alternative sets of variables from which you can become happy available. And the second one is one for this subsampling processes of monotone events. And yeah, just for people who care, I also wrote down like the precise LLL criteria under which these work, which are fairly standard in the field. But what I want to more highlight is that both of these LLLs, they actually work best when you use them in tandem. Right? You can use this sampling LLL to compute two sets of variables that you then use in the second type of LLL solver. And our full delta coloring algorithm actually really makes use of several iterations of these LLLs in the dense part. So I didn't talk about the dense part at all of the graph, which is actually the main challenge, in particular if you want to do it in the CONGEST model. But there we have lots of iterations of these LLLs to compute sparse set, and even to compute one of these sparse sets, we use several of iterations of this. So there's a lot that I didn't tell you and won't tell you now. So let me just summarize that in the end. What we get here, if you also take care of the dense part, we get such a polylog-log and round algorithm for delta coloring. We solve also with this approach quite a few other problems. And I want to just mention a few open problems. I wonder where else one can apply these LLL solvers. And I wonder whether such local sparsification is helpful elsewhere. I guess this degree range in many other models of computation is actually very easy, so it's a bit unclear whether it helps, but maybe there is some application. Of course, there are open problems for delta coloring and LLL themselves, and here the target is really to get to the lower bound and get log n rounds for both of these. Or for LLL, at least get it on bounded degree graphs, which also is known under the Chang-Petty conjecture. More general here in this field, we want to understand what can be solved in sublogarithmic time. And lastly, I just want to state an open problem that I actually like, and which comes to a surprise to many people in the field, is this delta plus 1 coloring, the greedy problem, which is much easier. For large delta, can you actually solve it in constant time, or do you need log star n rounds here? Because Lineal's lower bound of log star n is on the cycle. It can be extended to constant degree graphs, but it totally fails for large delta. So I really wonder whether we can do this and solve this problem here in constant time or not. And I'd say like answering this will give us a lot of new techniques, even so it's such a simple question here. So thank you very much. Yes, and I'm sorry for not saying anything about the dense part at all.
Does this give a new proof of Brooks' theorem, or do you use Brooks' theorem somewhere in the analysis?
It essentially gives a new one, but you need this LLL property to hold, so you need your delta to be at least a sufficiently large constant.
Thanks.
All right, so let's thanks again.